Hello viewers, welcome to the Substation Design 101 course. This course is geared to provide you with a comprehensive and broad overview of the entire life cycle of the substation design process, whether you are new to this industry or a seasoned professional looking for a refresher. The course has been broken up into 4 parts, roughly 1 hour each. Here is a brief outline of the course content. Part 1 of the course will cover the various substation types and their purposes, a brief overview of the substation design and construction process, followed by the initial steps in the design process, and finally the major equipment or building blocks that are key to designing any substation. Part 2 will cover typical foundation designs applicable to a substation, followed by a brief overview of the various structures utilized in a substation, and then delve into the preparation of single line drawings as well as present the various options for the substation bus configurations and their reliability indices. An important thing to note here is that if you are interested in digging deeper and learning more on any of these topics, then I would greatly appreciate that feedback and can create content exclusively to cater your needs. Moving on, in part 3, we will be looking into the process of converting the single line drawings to physical layout and some of the nuances around it. We will then cover substation grounding and the process for the ground grid design, followed by an overview of the substation protection and relaying, and finally discuss about substation commissioning, as well as providing some insights around the expansion, upgrades and upgrades of existing substations. Finally, in part 4, we will address the design aspects of a gas insulated substation, since parts 1 to 3 covered the air insulated type only. Before getting into the meat of the discussion, here is a list of the key references. The ANSI C37 and C57 standards are important in defining the major substation equipment. NEMA, NEC, and NESC are also useful. In many cases, the owner, that is the utility, will have their own set of standards and recommended practices, which are typically more stringent and onerous than the industry standards. If available, it is important to obtain them prior to starting the design process. A lot of times, drawings and design files from previous projects come in very handy. Substations can be broadly divided into 3 general categories, depending on their functionalities and purpose they serve. Of course, many variations of each may exist. Firstly, there are the generator step-up stations, which, as the name suggests, steps up the voltage from the generator terminal to the required transmission system level voltage. The generation in this case can be both traditional or renewable, such as wind or solar, or energy storage systems. Secondly, there are the transmission level substations or switching stations that serve as the heart of these transmission networks. Finally, there are the distribution substations, which steps down the transmission or sub-transmission level voltages down to the distribution level for serving the customer. Generation step-up substations are typically characterized by 1 or 2 very large transformers along with multiple HV or EHV transmission line exits, usually between 2 and 4, as shown on this illustration. In the cases of wind, solar, and energy storage systems, the medium voltage side of the substation is usually referred to as the collector station, since this is the termination point of the home run circuits that collect the power from these distributed generation resources, typically dispersed across a wide geographic area. A switching station is a substation without transformers and operate only at a single voltage level. As shown in this illustration, switching stations only have line terminals. Switching stations are essential in maintaining reliability of the transmission grid during contingencies and outages. On the other hand, a transmission substation will consist of both multiple line terminals and large power transformers. These transformers will step down transmission level voltages to sub-transmission or even distribution level voltages depending on the location of the substation and its application. Typical distribution substations will consist of multiple HV line terminals, transformers, and distribution feeder exits. These transformers are relatively small in terms of their MVA capacity. The feeder exits are usually radial. Finally, the electric service stations typically consist of a single distribution class transformer with a switchgear on its LV side serving multiple feeders. In some cases, these could be standalone breakers instead of an integrated switchgear. An optimized design process that serves multiple objectives is essential. The design must check several key boxes. Firstly, it must ensure high reliability by selecting the correct system level components and subcomponents, as well as ensuring adequate protection is deployed. Secondly, every opportunity to standardize the design should be considered. This reduces overall engineering cost across multiple substations, as well as reduces spare parts inventory and simplifies O&M. Finally, it must meet and sometimes exceed all applicable safety and environmental requirements. This includes the local, state, and industry standards. Next, let's look at an overview of the substation design and construction process. This is an illustration that summarizes the entire substation design, procurement, and construction process in a block diagrammatic fashion. In the later parts of this course, we will discuss in more in-depth some of these blocks. So we begin at the top left corner by first defining the system requirements and the purpose and type of the substation to be designed and constructed. This is followed by an initial project scoping meeting attended by multiple stakeholders, such as system planning, distribution planning, system protection, generation, substation operations, substation engineering, project management, regulatory affairs, and real estate. The system planner then develops multiple project solutions, including approximate costs with inputs from the stakeholders, and after the necessary revisions, assembles the final plan and project justification. The outline document of the proposed project is then routed for internal organization approval, followed by any mandatory regulatory review and approval, and is finally approved. This may take up to a few months. Once the project is approved, the project manager then develops the overall project schedule. The engineering cycle can then commence, led by the substation engineering and system protection groups, for the development of the required project drawings and study reports. Procurement of all major long lead items, such as transformers and breakers, must start very early on in the process to meet the desired timeline. Upon issuing the drawings for construction, the remaining items shall be procured. All below grade construction activities can commence once the civil drawing set is released, followed by the above grade work. This is followed by the testing and commissioning activities. Once the construction is completed, the drawings should be revised to reflect the as-built condition. At this point, the project is complete. This is an illustration summarizes the substation design process in a block diagrammatic fashion. This can be essentially broken down into 5 parts or sequences. Firstly, a high-level one-line diagram is generated based on the system studies and planning input. It is then used to create a more detailed single-line diagram, equipment plan layouts, and major equipment specifications. Next, the grading plan, the ground grid and grounding design, steel and foundation design, as well as the control house layout drawings are created. This is typically considered as a 30 to 50% milestone design completion. Next, to achieve a 90 to 100% milestone design completion, the deliverables are typically detailed relaying and metering diagrams, AC and DC schematics, including control logic, SCADA architecture, grading and drainage designs, as well as physical and structural connections and details. In some cases, wiring diagrams are required to be created for the fabrication of the protection and control racks. We now look at the crucial initial steps that are needed in the design process, which will help establish the boundary conditions. Prior to commencing any engineering activities, it is important to review the scope of work document to establish the project attributes. This includes the type and purpose of the substation, the major equipment being proposed, such as transformers, circuit breakers, number of lines and bus sections, protective devices, as well as the proposed site locations, and the status of procurement of the site. Additionally, need to consider all the regulatory approvals and their statuses, ultimate requirements for proposed facility, such as future expansions, and most importantly, the project budget. Next, we need to develop the project timeline for all the critical milestones and identify any critical paths to achieving on-time completion. This can be done in either Microsoft Project or Primavera P6. The critical milestones that need to be captured in the project timeline are the desired service date, and then working backwards, any regulatory approvals from the state and federal authorities, major equipment procurement, site acquisition if needed, applications with the transmission system provider, one-line drawing and site layout approvals. As well as critical milestones in the detailed design engineering process, which is typically broken down into 30, 60, 90, and IFC packages. And finally, the construction and commissioning sequence. As discussed in slide 13, this requires inputs and support from several key stakeholders, including project management, construction, engineering, operations, and maintenance teams. Prior to commencing the design engineering phase, it is important to gather some key information. If it is an existing facility, we need to make sure we have access to the complete as-built drawing set. This must include the one-line diagrams, site plan, grading plan, control building layout, control schematics, and SCADA architecture. It is also important to gain access to the latest design standards, if any, of the project stakeholders, since this will dictate what solutions are acceptable. In the event the existing station footprint requires expanding, we also need to obtain the legal description of the existing property boundary. Also, we should obtain the system planning studies since this provides the justification for this project as well as any future expansion requirements. The planning studies will also provide key pointers into major equipment requirements in terms of their ratings and specifications. An important early step in the substation design process is the initial site visit, especially for existing installations. It is crucial to take photos from all angles of all equipment and surrounding areas, including the equipment nameplates. Special considerations should be given to future expansions and any constraints associated with them. Need to observe and plan for any HV and MV power supply lines that will be brought into the substation, as well as how the proposed load circuits will exit the station. An important consideration here is overhead versus underground, or a combination of both. The civil engineer must observe the drainage patterns around the site. Depending on the location of the site, especially in urban populated areas, the aesthetic needs of the substation should also be considered. We need to also look for any potential environmental zoning and construction issues. An important consideration is the number and size of the transformers and the corresponding volume of oil and the containment needs. Sometimes the containment requirements are dictated by local codes and standards. Lastly, if the site is not yet purchased, then it is wise to look for a preferred option with one or more alternate options as backups. Following the site visit, there are several action items for the project team. The project scope may need to be updated depending on the findings from the visit. Applications to procure the site need to be submitted, as well as obtaining the complete project authorization and the notice to proceed. Preliminary one-line diagrams and site layout plans need to be prepared for stakeholder comments. Procurement of all long lead items such as transformers and breakers should also be underway. Geotechnical analysis and soil resistivity tests for the chosen site must be completed at this time. Next, we look at the building blocks or equipment that are required to design a substation. Here is a list of substation equipment classified under major, secondary, and auxiliary. Note that not all equipment listed here is required in every substation. We will take a closer look at the two most common equipment found in majority of the stations, and they are the power transformers and circuit breakers. This is the nameplate of a 34 to 69 kV power transformer in an energy storage system application. Typical nameplates consist of several key pieces of information on the transformer. Let's take a closer look at this nameplate. On the left-hand column, it shows the MVA capacity of the unit and the corresponding cooling class. This unit is base rated at 40 MVA with natural air cooling, also known as ONAN. Rated for 53 MVA with 50% of cooling fans operational, also known as ONAF stage 1, and top rated at 63 or 67 MVA when all cooling fans are running, or ONAF stage 2. Next important piece of information to take note is the vector group of the unit. This unit's vector group is uppercase Y, uppercase N, lowercase y, lowercase n, 0, D1, which means it is a grounded Y on the 69 kV side, grounded Y on the 34 kV side with a delta tertiary. This is also shown graphically at the top center of the nameplate. Then comes the impedance of the unit measured across the HV and MV windings, which is represented in percentage of the unit's base rating, and neutral tap position. In this case, it is around 8%. We will discuss more about the tap positions in a bit. On the right-hand column of the nameplate, we find a table with detailed information on the current transformers, or CTs, located in the transformer bushings. This table, along with the diagram in the center of the nameplate, provides information on the exact bushing location of each of these CTs, as well as their ratios and accuracy class and terminal details. The graphic at the bottom center of the nameplate shows the location of each of the bushings, as well as the location of the conservator tank and the tap changer relative to the main tank. Finally, let's look at the details of the tap changer, which is shown on the table presented in the top center of the nameplate. The tap changer is located on the HV side of the unit. The role of the tap changer is to ensure a constant secondary or MV voltage despite voltage variations on the HV side. This is a de-energized tap changer, which, as the name suggests, means that the unit needs to be de-energized to operate or change the tap position. It has 5 tap positions, with the middle tap, or tap number 3, being the neutral position, since it is at the nominal operating voltage of the system, that is 69 kV. It has 2 additional tap positions, number 1 and number 2, for accommodating above nominal system voltage, each at 2.5% increment, as well as 2 additional taps, number 4 and 5, for below nominal system voltages, also at 2.5% increment each. The optimum tap position should be chosen based on the prevailing system voltage on the HV side. Now let's look at the nameplate of a typical HV circuit breaker. In this case, it is an SF6 gas circuit breaker, which means that the interrupting medium of this equipment is SF6 gas. The 4 key items to look for are the rated maximum or line-to-line voltage, the rated continuous current, the rated frequency, and the rated short circuit current. In addition, we may need to pay close attention to the rated interrupting time of the device. In this case, it is 3 cycles, since a slow reacting breaker may adversely impact the system dynamics. The acceptable range for control voltage for tripping and closing of the breaker is also important, as well as their respective current draws, since this dictates the sizing of the substation battery and charger system. Rated voltage range factor of K equal to 1 means the short circuit current rating and the related required capabilities do not change with the operating voltage. While not shown in this nameplate, it is typical to present the bushing CT information as well, similar to what was presented on the transformer nameplate in the previous slide. This completes part 1 of the lecture series. Please stay tuned for part 2.